Here we are. Okay, wasn't ready for that. That's okay. Looks like the usual cast of characters. Wait for a little bit, see if more people come. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. How many people are in this class? Must be about 25. Not quite half. That's okay. Can I get a shout out from each and every one of you? Shout out. A hello? Oh, we're getting some claps. We're getting some chats going here. Shout out, yay. Hello, hello, hello. All right, life is good. Yvonne is here. Now we can start. Hello, Yvonne. Keegan Dupre. Leo Lee, Rock and Roll Lee is here. Sad boy is here. I'm sorry you're sad. I'm sorry you're sad. 1, 2, 3, 4 times 4 is 16. So we've got 15 people at this point. Who is sad boy anyway? Oh, Rachel Seller is sad boy. That's interesting. Okay. As usual, my faithful companion is here. If you have any dog-related questions, he's here to answer those. Buddy, okay, sit. Okay, lay down. No, I'm not petting you. You want to go out? Want to go outside? Want to go out? Want to go out? Come on, let's go. Let's go. Let's go. Come on, let's get it. Go. Yeah, go. Zooming with friends makes you sad. It makes me happy. This is the first time I've seen you people. And I still don't see any of you actually, but I miss the interaction. I do. Okay, shall we rock and roll here? Okay, so I don't know if you've looked at Moodle today, but I put a little quiz up there. So I was doing notes for today's lecture on Thursday last week, and I realized two things. Number one, there's not much left in chapter 5 to do. It's very short. And number two, I'm burning out over here. I don't know about you guys, but I can't do this anymore. I just can't do this. So I just thought instead of moving on to another chapter right away, we'd have a little quiz. So what we're going to do, I'm going to go through the end of this chapter, which is left-right symmetry. That shouldn't take more than 10 or 15 minutes. Then we'll go all the way back to the beginning. I'll review the whole thing. And then there's a quiz that opens up at 2:45, and it's open for 15 minutes. 5 questions, 1 point apiece. And they are bonus points. Everyone loves bonus points. So yeah, so that's it. So once I'm done with my lecturing here, that will open up. It will grade itself, and I'll add that into your bonus points for the class. Okay, questions? Preguntas, mi gente? Nothing? Nada? Nunca? Nadie? Nadie tienes nunca? Ninguno? Oh, I just said it like it was Italian. It's no, ninguno. Okay. All right, then. Let's share screen and get to work. Okay. Isn't it exciting when we get started? I'm excited. Okay, so let me see. I want to pull up the chat at the same time in case you guys have questions you want to load up on chat. Now, why am I doing this? What are you doing? What are you doing to me, mister? Chat. Shot. Oh, there it is. Okay. Le chat. I just went into French. Hey, Christina. Oh, you don't speak French. You're Italian. Oui. Okay, left-right symmetry. So 2 different models here. I told you we weren't going to do mouse. I lied. A little bit of mouse here. So what's going on here? Oh, you do speak French too. Of course you do. You Quebecois. So first is mouse. So this is kind of interesting. This is true in human too. Well, they don't talk about human at all, but I know it's true in human that if you have problems with your cilia, you have a 50-50 chance of having situs inversus, which means your organs are backwards. So normally, your heart's on the left, your liver's on the right, you're flipped the other way. So cilia have something to do with that, with where your organs end up. So, and this is why, here's Mr. Mouse. So this is like deep in the node. So as the node is coming back right down deep underneath it, the cells that are kind of leading the node, I guess, or as it's regressing, have got cilia, and the cilia are constantly beating to the left. So you've got nodal on both sides being expressed because you're into that area there. The cilia are beating to the left. Now, 2 different theories about why that matters. One is that you may be, because there's fluid moving this direction, you're pulling nodal from this side to that side, making more nodal over here. That's one idea. The other is you've got modal cilia, which are doing this, but you also have non-modal cilia. So when the fluid hits the non-modal cilia, they flip. And when they flip, that causes activation of internal calcium release. This is kind of how your ears work. The hair cells in your ears kind of work like this. So you've got these little cilia. When they move, you get calcium release. Calcium release then is tied into gene transcription a lot of times, and this is one of those times. And so you get more nodal being made, and so you got more nodal on the left than on the right. So that the key being asymmetric nodal expression. Oops, not this one. Hang on. So what that does then is nodal causes the upregulation of the transcription factor PITX1, I believe, PITX something. Yeah, so those non-modal cilia are mechanosensors. PITX2. So PITX2. I often wonder, when you've got a PITX2, does that mean there's a PITX1, PITX3, 4, 5, 6? I don't know. It's starting to bother me. But anyway, you get upregulation of that PITX1, and that causes left side organogenesis. So that's pretty simple, really. You got your cilia moving in this direction, activates signal transduction on that side, produces more nodal. Nodal makes left hand by upregulating PITX. Okay, chick, a little more complicated. Chicks are complicated. Just kidding, please don't report me for that. Okay, so in the chick, here we are, Henson's node. They say this happens in chick and xenobus. They don't know why it happens, but on one side of the node, you've got more activity of this hydrogen potassium ATPase. So because this is pumping ions, it causes a voltage, and there's less voltage on this side because there's less hydrogen ATPase than there is on this side. So you get a depolarization on the left side of the node because of less hydrogen potassium ATPase. and that causes calcium release, and not just release internally, but release externally. So it's releasing calcium out of the cell. That calcium causes activation of Notch expression. Hang on, let me look at that. I think it's actually delta expression. Let me check and make sure that's right. Notch ligand, right? So not Notch, but it's ligands. Notch, let's say, causes activation of Notch signaling by increasing Notch ligands. Okay. Remember, Notch is the receptor, and the ligands are delta and serrated. So you get an upregulation of delta and serrated that increases Notch signaling. So now on the left side, you've got more Notch signaling. Okay, so also the node is also releasing, this is from the node and the nodal cord, I think, releasing sonic hedgehog. So that's coming into play here as well. So then this is where the two different models converge. So because of Notch and sonic hedgehog, you get increase in nodal. So nodal is left-handed, is the left side. So you get upregulation of nodal, which increases PITX2, and then that becomes the left-hand side. Another kind of, two more things that kind of make this stronger, whatever the English is for making stronger, are that you get activin on the right side that's inhibiting sonic hedgehog. Activin, remember, is a TGF-beta-like hormone. They don't say why activin's preferentially expressed on the right-hand side, but it is. Blocks sonic hedgehog, which blocks left-handed stuff here. Here's another thing that's confusing me, so we're not going to worry about it too much between me and you guys. Lefty. So remember way back in mouse early gastrulation and stuff, lefty was being expressed, and lefty blocks nodal activity. That was when we were making the AVE on the anterior side of the mouse early embryo. So lefty here is also blocking nodal. And so that makes this side left and that side right. What confuses me is this figure, and also the figure legend, so it's not a mistake. They put lefty on the left, and they're saying lefty on the left is blocking nodal activity on the right. I don't know. That doesn't make sense to me. I would expect lefty to be expressed on the right and block nodal on the right, making that right-handed. Instead, it's lefties on the left, blocking nodal on the right. What are you going to do? Okay, that's about all we have for today. Like I say, there wasn't much, but it was Thursday afternoon, and I was just burning out, and it's like, I got to do something else on Friday because I can't do this another day in a row. So what I did was make sawdust in my basement, which was fun. And that's all we have for this, chapter 5. That was an easy chapter, wasn't it? We just kind of buzzed right through that. When I first set up the syllabus, I looked at, oh yeah, this is good, this is good, oh yeah, this is good, this will lead, I had about 10, usually I get 2 chapters in per lecture in cell biology. So yeah, let's say about 8, 9, maybe 10 chapters we'll get through. We've done 3. So I'm thinking about moving on to chapter 10 at this point. Chapter 10 is less about signaling and more about how when cells are moving, they're tugging on each other, and this tugging causes shape changing and how that's important in developing the embryo as well. So we may go there. Julia, is the bonus quiz going to be based on what we talked about today or chapter 5 in general? It's going to be on the second half of chapter 5, not the first half, but the second half. And that's what I'm going to do now. When I stop talking, I'm going to go over the whole second half of chapter 5. So when we have our exam the week after, during finals week. So we still have 1, 2, 3 more lectures before exam. And that exam will be on the second half of chapter 5, plus whatever we do between now and then, which hopefully won't be a lot. Okay. All right, so shall we start over again and right from the beginning of second half of chapter 5? Can I get a thumbs up from people? Got Adelina's thing. Yes, yes. Okay, so the dog wants to come in. Hang on. He loves me, and to be honest, I can't blame him. I really can't. Okay. All right, so starting off the second half, we start off where we left off. Well, we left off talking about in the previous thing about where is it? This. So in the first half of chapter 5, we left off talking about how the node is moving and posteriorly, and it's also producing FGF and Wnt. So you've got this gradient of FGF and Wnt that goes from the node, like it's kind of like staying there as the node goes away. So you've got this gradient of FGF Wnt. And also you've got cells differentiating, producing a gradient of retinoic acid. So, and that's causing our differentiation. And we didn't say much more about that. So we started out figuring out what actually is happening there. So we're doing anterior posterior patterning. And here is our check right at the beginning here. So this is the node, Henson's node. And we've got a number of things going on here. You've got this, let me blow this up a bit. I'm assuming you can see this the way I'm seeing it. I hope you can. Over a tad. Stay there. Okay, so what we've got going on here is you've got these kind of this tan area here, which is some cells in the node itself, which are forming the notochord. So that's mesoderm is being induced here and forming the notochord. And then across the top, you've got other cells that are coming from the stem zone. So these are not stem zone cells, but these are stem zone cells. And these are neural cells, which then will come up and form the neural plate. And underneath those neural cells, we've got other cells, which will be axial mesoderm. So these mesodermal cells are coming out this way, and they're going to form the somites. So you've got kind of neural tube or mesoderm coming in, forming the notochord. Across that top of that, you've got neural cells, neuroectoderm coming in, being induced to become neural floor plate. What is it? Neural plate. And underneath that, you've got cells coming in kind of under and to the side, and they're becoming mesoderm. Now, as this node is regressing, you've got a gradient of FGF Wnt here, and all these cells hit a certain spot where suddenly they stop dividing, they stop being mesenchymal, and they differentiate into somites or neural tube or whatever it is they're going to be. So keep in mind the difference between mesenchymal and epithelial cells here, because mesenchymal epithelial transition is one thing. We see cells do that a lot. We also see mesenchymal epithelial transitions happening. So that's what this is. These cells are mesenchymal. They're here being hit with a high level of Wnt and FGF, so that makes them mesenchymal. They're dividing and they're moving. They move out this way, they get into place. Suddenly FGF drops off and they transition from mesenchymal into epithelial cells. So mesenchymal cells are not grabbing other cells, they're grabbing extracellular matrix and crawling along it. Once they become epithelial, they set out these CAMs, cell adhesion molecules, and they grab other cells, and now they're locked into place as a tissue. And that's what chapter 10 is about. So we're going to be talking about that in chapter 10 a bit. So out here at this determination zone, determination wave, out here, they're transitioning from mesenchymal into epithelial cells and also from kind of generic mesenchymal cells into somites. So that's where your differentiation is happening. Okay. Now, that's as the node is regressing. Out in front of the node, though, if you remember, the node kind of starts, and the first somites are like around hindbrain. So everything that happens forward of the hindbrain is happening because you've got mesoderm here. Oh, shit. Sorry. Shoot. Where am I? Jesus Christ. Oh, here we are. Okay. So if you remember, here's your hindbrain. This is kind of where the node is starting. Out in front of that, you also have different development happening because these cells that are coming in the sides, like the ones that are coming in and going out laterally, they're going anterior and lateral. So they're going ahead of that node and they're going to form the head process. So those cells came in like through the node and they come out here and they're going to induce the ectoderm above them to become the brain. So that's going to thicken up and become the brain above there. So all that, everything forward of the node is happening because of those mesenchymal mesenderm cells crawling in and going into that area. And then here we're coming back to this, which I redrew because I like this way of looking at it a little bit better. But this is what I just talked about a few minutes ago. And here's our DW. Oops. Where is it? It doesn't say it here. It'll say it later. But the differentiation wavefront is right here, where that FGF drops off. Okay. All right, so somites. Now we're going to make our somites. So let's see, to begin with here, we're just saying, I think all we're saying here is that somites are just a segmented pattern, which is kind of an evolutionary history from insects, which are totally segmented. These somites are separated from each other by notch signaling. We'll talk a little more later about notch signaling being used for anterior-posterior patterning in somites, but that's what causes them to separate, and they form this like cup-like structure. So it's not straight across, it's like cupped, big deal. Okay, and this notch signaling, another signaling pathway. I'm thinking this class should be taught after cell biology because this is all cell biology that it would be great if you knew it coming in. But anyway, notch signaling is basically the receptor is notch and it's a transmembrane protein. And when this is called juxtacrine signaling, when you've got one cell touching another cell and the ligand is on one cell and the receptor is on the other. So the ligand here is either delta or serrated. When that touches notch, that activates a protease in the cytoplasmic side of notch. A protein comes off, and that's a transcription factor. So that's all there is to notch signaling. Pretty easy. Now this is talking about AP patterning of the somites, and this is like, if after that node has passed, if you take out the somites and flip them over, they come in backwards, which tells you that the pattern is there. And even if you take it not at the somite side, but at the pre-Semitic mesoderm side, you don't even have somites yet, the pattern is already there, because if you flip it, you get an upside down segment to your embryo. And nobody likes that. Okay, so here this is showing how it's upside down. 9 and 10. We'll come back and refer to 9 and 10 again later. And here's our wavefront, determination wavefront. And this is because, it's a wave, which means it's not something that's there. It's something that's moving. I don't know. But you've got your node, which is making FGF and Wnt, and it's moving. And as it moves, it lays down FGF and Wnt. And it's highest at the node and less as you get further and further away from it. And then you get and then you've got RA coming from the other side, from the already differentiated somites. And you get that one point in the middle where FGF is still there, but it's low, and RA is there as well. So they're both there at a low level. And at that point, boom, it differentiates. And that's your determination wavefront. And there's a nice animation there you can see someday. And then this is another interesting thing too. So as the node is going this way, the cells in that presemitic mesoderm are cycling these genes. They're coming on and going off, coming on, going off, coming on and going off. And they're cycling faster than the node is moving. And these things are cycling because you've got FGF there. FGF is upregulating Wnt. Wnt is upregulating Notch. Notch is upregulating Hairy. Hairy is upregulating Ephrin A1. And Ephrin A1 causes somite formation, but only after you get past that determination wavefront. So this cycling happens over and over again as the node is moving until the cells that are cycling hit that wavefront, and then they differentiate. And this is kind of important because this is important, especially in terms of evolutionary development. If you look at different animals and how different animals have different numbers of vertebrae, it has to do with that cycle rate versus the node rate. If the node is moving at a constant rate, but the cells are cycling faster, you get more somites that are smaller. If they're cycling slower, then you get fewer somites and they're bigger. So the difference between the node movement and the cycling rate determines how many vertebrae you're going to end up with. So that's kind of important. And the reason they're cycling is because of these feedback mechanisms. FGF activates Wnt, Wnt activates Notch, but it also activates Axin, which blocks Wnt. Notch activates Hairy, but it also activates MSP, which activates lunatic fringe, which inhibits Notch. And so I just made these numbers up, 30 minutes, but you think about it this way, it makes sense. FGF makes Wnt, Wnt makes Axin, and that takes 30 minutes. Axin shuts off Wnt. Axin stops being made because there's no more Wnt signaling. That takes 30 minutes. Axin gets degraded. Cell's ready to respond to Wnt again. There's your next 30 minutes. Wnt comes in, start the cycle over. So you've got this clock that goes based on those reactions. We're doing this again for some reason. Okay, so this is just talking about the patterning that's there, the AP patterning, and this is why we've got AP patterning. Okay, so as this node is moving and you've got your clock generating the number of somites here, you also have waves of gene activating coming from posterior to anterior. But what I mean by that is the cells aren't moving, but these cells start to express HOXA1, then these cells express it, these cells express it, boom, boom, boom. So it's a wave of gene expression. And that wave of gene expression going in one direction meets the movement of the node in the other direction. So then as your node is moving, each somite gets encoded with a different series of HOX genes. So these HOX genes, you've got 4 different groups or clusters of HOX genes. They get transcribed from 3' to 5'. So your anterior end ends up with all the 1 paralogs. Paralog, that's a great name, paralog. So all the 1 paralogs here, and then as you go back, you get the 2 paralogs, the 3s, and so forth, until you get all the way to the tail bud, which is expressing the 13th paralog. Paralogus. Okay, so here you can see mapped out on the embryo how these genes get laid out and get expressed. I mean, throughout the body. And the anterior end of the activation of these genes is very distinct, but once they're on, they kind of stay on all the time, although they go down in amount. So your most anterior regions have got the highest, have got only the expression of your first paralogs, the HOXA1, your HOXB1, your HOXD1. You get into the next segment, the I can't read that, cranial maybe, I don't know. You start getting more HOX genes turned on. So each segment then is going to be patterned by the combination of HOX genes that are on. So if you look at something here in the lumbar, you've got all these HOX genes on at low level, these at medium level, and these at high level. And that tells those cells, you are a lumbar. And your life's going to be hard because all the weight of the spine comes down on the lumbar. Keep that in mind. Okay. And then this is overlapping expression. Oh, this is showing how across, no, it isn't. The next one is across different species, you get the same HOX genes representing the same part of the body. Although here, chickens have got longer necks than mice. So, you know, your clock is moving at 90 minutes versus the mouse clock is moving at like 20 minutes or 2 hours, I think. So you get a lot more cervical somites here, but it's the same HOX genes expressed in the cervical vertebrae or the cervical somites as it is in the mouse and the chick. And here's my, stop that. Here's my animation. And again, what this is trying to show is the wave of expression of one coming up and hitting the node, getting encoded into a somite. Now the wave of expression of the two paralogs are coming through, hitting the node as the node regresses, getting put into somites. Wave of ortholog, or paralog number 3, getting put into somites, and that continues until the node makes it all the way to the end. And that's your AP patterning via HOX genes. By the way, if anybody's got questions, I know I'm going kind of fast. If you got questions, just go ahead and type them in the chat or turn your volume on and give me a yell. Okay, so this is talking about, this is the next lecture when we're talking about why these HOX genes get turned on in that direction, in that order. And it's because it's kind of like dominoes falling down. The winch from the node turns on the first ones, the one paralogs, and then the one paralogs activates CDX2, which activates the next ones. And I think it's probably more complicated than this, but this is all your book says. And then, because it's got to be more than just Wnt, CDX2, and then HOX13, but you know, there's probably other things along the way that are being turned on by previous HOX genes that are turning on later HOX genes until you get all the way to the end and HOX13 shuts all the other ones off. So that's how you're getting that progression as the waves of expression are going. Oh, by the way, I went through my notes and corrected them and stuff, and I moved some stuff around. Hopefully you're not printing these out. I noticed that a couple of lectures I ended, and then the next lecture I started with about 5 minutes of something that belonged in this lecture. So I cut it, pasted it up there, kind of reorganized a bit, but it's all there. I took out the things that were definitely lies too. I threw a few lies in there to keep you on edge, but nobody picked up on it. Okay. I'm learning from our president on how to teach science. So anyway, here we are, patterning of somites. So, you know, you've got your anterior, posterior patterning, but even within one somite, you've got anterior side versus posterior side. And that's done by notch signaling again. So you've got delta and notch being expressed on the anterior side, and that gives you notch signaling on the anterior side. On the posterior side, you've got MSP2, which is upregulated by notch but inhibits notch, if you remember that feedback, that negative feedback pathway from the clock situation. Okay, so you've got MSP2 upregulated on the posterior side, and that blocks notch signaling. So you've got high notch here, or high notch ligand here, and then low notch signaling over here. And that gives you these stripes, which is your anterior posterior patterning. That's far less interesting than dorsal ventral patterning. It's there. There it is. There it is. That's all I'm saying. Okay, dorsal ventral patterning. This is a lot more interesting. And there's a really good, I think there's a pretty good video on this too listed. So here's your somite. Call this just a generic somite. Pretend it's not blue on this end. So this is your general somite. Now this has to go into a lot of different tissues. So it's going to be getting signals from different places to go into those different tissues. It will get Wnt from the top, which is going to give you a dorsal ventral Wnt gradient, and high Wnt is going to give you dermal myotome. Dermal myotome will become the dermis, which is the kind of skin underneath the epidermis. So that spongy part of the skin. You've also got sonic hedgehog coming from the bottom, okay, coming from the bottom of the neural tube and from the notochord. And that's going to make these cells into that sclerotome. And sclerotome becomes the bone, right? Sclerotome will be chondrocytes and then osteoblasts, and it'll become the vertebrae and the ribs. So vertebrae and ribs then are being induced by the sonic hedgehog. And then your mesoderm from the side is always releasing BMP4, which is forming a gradient coming in. We'll see this again in the next lecture with neurocrest cells, okay? So you've got BMP4 coming in from the sides, which is patterning the what do we call it again? The dermal myotome in the middle. So the middle dermal myotome ends up as myotome, and that will then be patterned by the BMP4 into medial mesodermal structures and lateral mesodermal structures. So that myotome will become back muscles on the medial side, and it'll become abdominal muscle and limbs on the lateral side. So that's because you were BMP4 gradient. Easy. And here's sonic hedgehog. So you should know this as well. There's a really good figure on this in chapter 10 if you have the book. I think I may put that in as the last slide in this. I didn't want to insert a slide, then I have to go through all my notes and change all the slide numbers. I should have, but I didn't. But anyway, here is you've got these primary cilia, which are not modal cilia, they're other cilia, and they've got this protein gli in them. Smoothen would allow it to be released uncleaved, but patched is blocking smoothen from getting up there. So gli is sitting here, it gets cleaved, and the protein made from gli is a repressor, blocks genes. When hedgehog is around, sonic hedgehog, it blocks patched, smoothened, which is in a vesicle, goes up into the membrane, goes up into the cilia, blocks that cleavage of gli. Gli comes out as a different protein, and now it's an inducer. So you got that. Mainly you want to know that hedgehog, for this class, let's just say hedgehog signaling, okay? Let's not worry about the pathway. It's not that important right here. Okay, remember I told you BMP4 is coming in from the lateral side? Here it is again. So here's your notochord inducing neural plate, and neural plate then will form the neural groove, which will then become the neural tube, and then the top of the neural tube becomes neural crest cells. Now these are the figures from the book, not as detailed as the ones I got from that video. So let's do it from the video. Here is your notochord. Notochord induces the ectoderm above it to become neural plate. Now you've got BMP4 coming in from the sides of this. And so here in the middle, right here, you've got an area where you've got FGF being produced out here by the notochord. And then you've got like high BMP4, which is blocking Wnt signaling, not FGF, Wnt, blocking Wnt signaling to stop the neural plate from like covering the whole body. So over here, BMP4 is blocking it. Over here, Wnt is making neural tube. In the middle, you've got low Wnt, and that is being something middle-ish, and that middle-ish thing turns out to be neural crest. So it'll be the top of the neural tube when it folds up. And then here's the top of your neural tube, which is the neural crest. Now at this point, now you've still got, let me check this to make sure I'm not saying something stupid. Oh, I don't have the notes here. Oh, Dr. Slush, you could never say something stupid. Everything you say is so smart. Get out of here. Oh, stop. My daughter. You're a troublemaker. Okay, FGF. Been saying Wnt, I should have said FGF. Okay, so start over real quick. Get out of here. Okay, start over real quick. Here, we've got FGF signaling, and then we've got Wnt signaling, or FGF signaling, BMP signaling, and then here you've still got FGF, and now you've got more BMP4 because that epidermis is covered, and now right here you've got a lot of BMP4 hitting those neural crest cells, and that, my friends, is causing the epithelial to mesenchymal transition, okay? The opposite of what we saw before. Instead of mesenchymal to epithelial, now we've got epithelial to mesenchymal transition. And now these neural crest cells can start to move. And boy, do they move. They go everywhere, and they make a lot of different things. But they still have the patterning from the Hox genes, and they go off and they form stuff. Okay? I kind of finished that up quickly because it's time for your quiz. Now, let me give you a quick warning about this quiz. You got 15 minutes. Don't look up the answers. Go through all the questions, answer them all, then go back and look at your notes and see where you went wrong. Okay? Why don't you guys go ahead and rock on that? And I'm going to stop this chat now, okay? Love you guys. Good luck. When does it due? It's done in 15 minutes. You got 15 minutes. It's due now. Later, dudes. Later, dudes. Has it stopped yet? End meeting for